Welcome to Matrix Operations, section 2.1. I don't know if you remember that game Operation or not from when you were young. I don't know if they still make it or not, but it looks something like that picture above. Okay, the only thing really interesting today is matrix multiplication and transpose. Matrix addition, scalar multiplication, notation, that's pretty straightforward. Nothing too exciting is going to happen. So if you have a matrix M by N, you can describe it by denoting the columns, in which case you're going to write it like this, C1 space C2, where each C1 stands for a column of A, and there are N of them. Or you can denote the rows, row 1 through row M, or you can denote each entry. So in this example here, this would be, obviously, row 1, first row. This would be column 3. And this entry right here is A sub 3, 1. So the first number denotes the row, and the second number denotes the column. So if you're in the third row, first column, you're at -1. 0 stands for the zero matrix, and that can be any size, and you're just going to have to go by context. The identity matrix is denoted by a capital I, and that has to be square. So n by n, square. I don't know why this keeps erasing square. So here's some examples, a 1 by 1, a 2 by 2, a 3 by 3. Notice that the ones go from top left to bottom right. Reduced echelon form. Okay, so let's do some addition and scalar multiplication computations. We've got 3 matrices here, A, B, and C. If I want to add A and B, I can, because they're both 2 by 3 matrices. They have to have the same size. And by adding entry-wise, that just means you're going to add the entries of the first matrix to the corresponding entries of the second matrix. For instance, I'm going to add 1 to -1 to get 0. And then the second entry going along the top row is 2 plus 2, which is 4. And then the third entry on the top is also 4. And then moving to the second row, I want 4 plus -3, which is 1. 5 plus 1 is 6. And 6 plus 2 is 8. Okay, next one is a difference of 2 matrices, and in each case I've multiplied the matrix by a scalar multiple. So 2C, and I've written down twice, and then this is the matrix C, minus 3I, and there's no ambiguity there. Since C is 2 by 2, this I here has to be a 2 by 2 I. So I put in 3, and then this is, you could denote it I sub 2 for 2 by 2. And so now let's distribute before we subtract. So when I take a scalar multiple times a matrix, I multiply every single entry in the matrix by that scalar. So 2 times 2 is 4, 2 times 1 is 2, and then on the second row, I have -2 and 6. And then I'm going to subtract, I'm going to multiply 3 by these ones here to get 3, 0, 0, 3. And now I can subtract entry-wise. On the top row, 4 take away 3 is 1. And then 2 minus 0 is 2. And then -2 minus 0 is -2. And 6 minus 3 is 3. So fairly straightforward. The next one I can't do, because I'm taking a 2 by 3 and I'm adding it to a 2 by 2. So this is a 2 by 3, 2 by 2. You can't do that. You certainly couldn't add entry-wise, because you have a different number of entries in the first matrix as you do the second. That would be like trying to mate a cow with a bunny rabbit. You just can't do it. All right. algebra rules for addition and scalar multiplication. I'm not even going to read them. There's no surprises here. Everything you would expect to be true is true. You've got commutative, you've got associative, you've got certain distributive laws. And here, the distributive laws apply to how scalars distribute over matrices. So I said I wasn't going to read this, so I'm not. Okay, so moving on. Matrix multiplication is going to come in two parts. One, how we're going to do it in practice. That's what I call the row dot column rule. So dotting the rows with the columns. So this is an extension of how we multiply a matrix times a vector. So there should be no surprise there. And then the second part is the definition of matrix multiplication, which we will use in theory, but not in practice. So here's how the dimensions work. If I have an m by n matrix, A is m by n, I can multiply by any n by p. The inside dimensions have to match. Okay, they have to match. So that red dimension has to match. The columns of A has to be the same as the rows of B. And when you multiply, that inside dimension cancels out and you end up with the two outside dimensions, m by p. And the way you're going to find that product is you're going to just think of the second matrix B as a bunch of columns. The first column of the product AB will be the whole matrix A dotted with the first column of B. That's not making a lot of sense, so I'm just going to show you what I mean. Multiply using the dot product. So pretend the second column isn't even there. If it weren't there, we would know exactly how to do this. So this is a 3 by 2, and I'm multiplying by a 2 by 2. So my final matrix will be a 3 by 2. 3 by 2. So we're going to start by doing the first column, and then we'll do the second column. The first column of the product is going to come by looking at only the first column of your second matrix in the product. So I'm going to take this first row and dot it with 2, 3. So negative 2 times 2 is negative 4, plus 2 times 3 is 6. Negative 4 plus 6 is 2. Now I'm going to look at the dot product of this blue row with 2, 3. So 2 minus 9 is negative 7. Now I'm going to look at the pink row, and I'm going to dot it with 2, 3. You get 2 times 0 is 0. 3 times 1 is 3. Okay, I've got my first column. Now, pretend let me erase this. Pretend the first column doesn't exist, and we're only going to look at the second column. That's how we're going to get the second column of the product. I'm going to take the first row of A, the yellow row, and dot it with negative 3, 1 to get 6 plus 2 is 8. Now I'm going to take the second row, dot it with this column, negative 3, 1, to get negative 3 minus 3, which is negative 6. And finally, I'm going to take the pink row, dot it with negative 3, 1 to get 1. And that is my product. So what I want you to do now is pause the video, fill these out, do these yourself, and the answers are at the end. Check yourself and make sure you're doing it right. I mentioned that it's helpful to find the dimensions first. For example, this is a 2 by 3, and I'm multiplying by a 3 by 2. So I know my product will be a 2 by 2. And it's going to have 2 columns. The first column you're going to find by ignoring this column and dotting the rows of A with this column. So there'll be 2 dot products. For example, the first entry, I can't stop myself, is going to be 4 plus 12, 18. 12, 13, 14, 15, sorry, 16, LOL. Okay, then, so you fill in this entry, then you're going to ignore the first column of B and focus on the second column, and that will give you this column here. So I don't want to go on until you've done that, so make sure you can do matrix multiplication. Okay, so hopefully you've done that. So now let's talk about the definition of matrix multiplication. So again, this is not something you're going to do in practice, but it is important. If we have an m by n and we multiply an n by p, so the dimensions have to work out, then AB is the m by p matrix whose columns are linear combination of the columns of A using the weights from the columns of B. That's a mouthful. So symbolically, the first column of AB is the matrix A times the column B1. The second column of the matrix AB is the matrix A times the column B2. So I want to show you what that looks like with an actual example. And the example I'm going to use is the one we just did up here, where we did, stop. Okay, I'm going to use this example again, this A and this B that we did at the top there. Okay, so I've done the computations for us, so we can just read along and see what's happening. According to this definition, I'm trying to make this bigger, the first column of my product matrix is AB1. So here I have the matrix A, and I put in the column B1. B1 was 2, 3. And now what I'm going to do is use the definition of matrix vector multiplication, not the dot product one that we've been using, but the actual definition, which says I use the columns of A and weight with the entries of B. So twice column 1 plus 3 column 2. Note I get 2, negative 7, 3. That should be the first column up here. Yes, it is. That we got using the regular good old dot product. And then second column of the product is A times the second column of B. And then my weights are negative 3 and 1. So I take the columns of A and weight with those weights, add together, and I get what I got before. So it's important to know, that the product is has columns which are linear combinations of the columns of A. But it's not important to be able to do matrix multiplication this way, because you're actually not going to do it this way. You're going to do it like we did at the top. Okay, properties of matrix multiplication: associative, left distributive, and right distributive in terms of multiplication. And the reason why we need two different distributive laws, left and right, is because we don't have commutative. So the big surprise there is that AB is not BA in general. So that's why it's missing from this list. What's important in this list is that you can do associative, you can do distributive as long as you're careful and just keep the order the same. Like you can distribute A to B and A to C. Just go A, B, A, C. You can't switch the order. Let me jump down to this one. The identity times A is A, which is A times the identity. But the identity on the left doesn't have to be the same as the identity on the right. If A is M by N, then to multiply on the left by the identity, that would have to be the M by M identity so that the multiplication made sense. So on the left, we have IM. And on the right, if again, A is M by N, on the right, I need to multiply by an N by N. So this is IN. So let me show you an example of that. Let's go 1, 2, 3, 4, 5, 6. There's my A. And I want to multiply by a matrix on the left to get A again. 1, 2, 3, 4, 5, 6. So I claim that over here, I'm going to put the 2 by 2 identity. 1, 0, 0, 1. Okay, so let's just make sure mentally that works. What I'm going to do is ignore these two columns of A and focus on this column. And I'm going to dot this row with the first column to get 1, and that's my entry here. Now I'm going to dot 0, 1 with 1, 4, and that's my entry there. So the first column looks good. Now I'm going to ignore the 1, 4. Let's see if I can erase that. 1, 2, 3, 4, 5, 6. Ignore this guy, focus in on this guy. Dot with the top row, get 2. Dot with the second row to get 5. And I'll let you verify that the third column works, but it's interesting. You get a matrix times A is the same matrix, but that matrix is the identity, but you have to have the right size identity, so the matrix multiplication made sense. And if you want to multiply A on the right by an identity to get A back again, since A is 2 by 3, on this side, you need this identity, the 3 by 3. And you can verify, you should do that, verify if you multiply A by I3, that you'll get A back again. All right, so the surprises are, commutative property does not hold. The cancellation property does not hold. Typically in algebra, if you have you know, two, well, let's see, let me think of a good example. Okay, 2 times 3, if that's equal to 2 times x, I can cancel the 2's and say, oh, x must be 3. You can't do that with matrices because it might not be true. Zero factor property is related to that. If the product of two matrices is 0, that doesn't necessarily imply that A is 0 or B is 0, that one of the two factors is 0. In algebra, we do have the zero factor property. For example, if x plus 2 times x minus 3 is 0, then we know either x is -2, this factor is 0, or x is 3, this factor is 0. Don't have that with matrices. So in the practice problems at the end, you're going to give you an A and a B, and you're going to show that AB is not equal to BA. Let's look at this one. If A is 5 by 3 and AB is 5 by 7, what is B? So here's A and here's B. This is super easy. B has to be 3, so the inside dimensions have to match. 3 by something. Well, to figure out what that something is, we go over here. The outside dimension of the product is 7, so that has to be a 7. So B is 3 by 7. All right, winding it up, matrix transpose. This is an important operation we can do on matrices. What we do is we convert the rows of A to columns or the columns to rows, and that's how we get the transpose. So for example, if A is this matrix here, A here is 2 by 3, the transpose is going to be 3 by 2. And the way I get the transpose is I take the rows of A, so the first row of A is 1, 2, 3, I turn it into the first column of A transpose. And then I take the second row, 5, 6, 7, 5, 6, 7. That's the second column of the transpose. All right, so switch the rows and the columns. So here we have a 2 by 2. So the transpose of a 2 by 2 will also be a 2 by 2. What's going to happen is this first row, 5, 1, turns into the first column. And the second row, 3, -2, turns into the second column. All right. if A, and here A is 2 by 1, the transpose is 1 by 2. So the transpose, I'm going to take the first row of A, which is 1, turn it into the first column of A transpose. And then the second row of A, which is 5, I turn into the second column of A transpose. So same entries, but they're in a different order. And then if you have a 1 by 1, its transpose is always itself. So if you take a 1 by 1 and transpose it, you get the same thing that you started with. Okay, so I just want to reiterate, probably the most important thing we're doing today in terms of your success for the rest of the semester is multiplying matrices. So you have to be able to multiply two matrices. And if you are successful multiplying a matrix times a vector, 6, 1, if you were successful doing computations like that, you'll be successful doing computations like this because it's an extension of computations like that. Okay, just had to get that in there. And then let's just look at the properties of transpose. Some are interesting, some shouldn't be a surprise. If you take the transpose of a transpose, you'll get your matrix back again. That should make sense. You switch the rows and the columns and then switch them back again, you're back to the beginning. This one can be easily verified. If you add two matrices together and then take the transpose, that's the same as first transposing each matrix and then adding. This third one I can explain. If I take a matrix A and I multiply every entry by 2, then I transpose it. That should be the same as if I just first transpose the matrix, then multiply every entry by 2. In each case, every entry is being multiplied by 2. So I think that one should be pretty clear. And then I wanted to just look at D in terms of, I'm not going to prove it, but in terms of dimensions. Let's suppose A is 3 by 5. So A is a 3 by 5. And B would have to be a 5 by something. Let's make it 5 by 7. Okay, so the product AB is 3 by 7. So what's AB transpose? AB transpose, if you take the transpose of a 3 by 7, you get a 7 by 3. So I'm just verifying the dimensions on the left versus the dimensions on the right. Now let's look at B transpose. B transpose is going to be a 7 by 5. And if I multiply on the left by A transpose is a 5 by 3. Notice those inside dimensions match. The 5s match. That's great. And so B transpose A transpose is 7 by 3. So in fact, they're equal. B transpose A transpose is equal to AB transpose. Now, by showing that the dimensions are the same, I haven't shown they're equal, but that is a nice thing to know. Oh, well, at least the dimensions are the same. Notice if you tried to stay in the same order, if let's say you thought that AB transpose was supposed to be, which it's not, A transpose, B transpose, the dimensions might not even work out. In fact, in my example here, if I took A transpose, which was a 5 by 3, and I tried to multiply by B transpose, which is a 7 by 5, I couldn't even do that product. A transpose times B transpose isn't even defined. So you have to change the order in order to multiply. Okay, then I've got a bunch of practice problems for you. Here you have to compute a power. Note that you're not going to distribute that 3, so I went over it kind of quickly, but up here, powers, if you have A squared, that means literally you have to multiply A by A. So A cubed is going to be A times A times A. Negative 3, 1. This would be A cubed. And there's no way to do that all at once. You can't just say, oh, this is the answer, blah. right? What you're going to have to do is first do one product, the 2 by 2 times the 2 by 2, find that, and then multiply by the last matrix. So it's going to take a little time. Imagine what a drag doing a 4 by 4 would be. Very much so a drag. Okay, and then you can read through the rest, and that is the end of this section.